So we talked briefly about the most basic application in classification. And one of the things we've said a few times here is that in doing this, the way that this procedure ought to work is that you have some data you use as the so-called training set, training data, and then other data that you use as the test data. And so here the idea is, right, I have some data that I collected from the two conditions I'm interested in, plot them in the space of the voxels, learn usually, but not always, a linear plane that's the best way to divide those two in the training data, and then take some new data point and ask, based on what I learned in the training data, what condition do I predict that that new data point comes from? And then check whether I was right or not, right? Check whether, in fact, when I predicted that it was from the green condition, it was from the green condition. Okay? So to use an example from a paper that Amy Scarry and I did, for example, we could imagine participants were in the scanner. They were looking at faces. The faces showed emotional expressions. And so over 7 runs in this case, right? 7 runs of training data. So we get 7 beta values in each voxel for the sad female faces, 7 beta values in each voxel for the happy female faces, right? And then when we test within female faces, sad versus happy, but now this is in the left out run, right? So this is in one other run of data. So a new beta value taken on in a different run of data after we've stopped, taken a breath, start again, scan for whatever it is, 5 minutes. You see a bunch more faces. We take the beta values in that new run, and we ask whether the predicted classification from the training data is accurate in this binary task in the test data. So we'll often get 2 answers, right? We give it the female sad data and say, do you say sad or happy? We give it the female happy data and say, do you say sad or happy? So you can get an accuracy score in that iteration of 0. You got it wrong both times. 1, you got one of them right, one of them wrong. Or 2, you got them both right. Is that clear? So in one iteration of this, get a score of 0, 1, or 2 for a brain region, right? So we'll think about this again. We set some local region, right? In this experiment, one of the regions was in medial prefrontal cortex. And there's medial prefrontal cortex right behind your forehead. So one region of interest we had was in medial prefrontal cortex. With that brain region, we defined it independently based on independent functional criteria, and then drew features from it based on signal-to-noise ratio. So that was a functional region defined as a local region, and then feature selection for statistical purposes, right? We pulled high SNR voxels. And in one iteration of this classification test, you get a score in that brain region, right, those features, of 0, 1, or 2, right? And then the first thing is, this whole procedure 8 times, right? So that means you got 0, 1, or 2 the first time we did this, and then we switch which run is the left out run, right? So we take that run, we put it back in the train, take a different run, put it in the test, train on the 7 runs, test on the left out run. So now a brain region's classification score is from 0 to 16, right? Is that clear? So for one person, for one classification, the score is from 0 to 16. In fact, we would probably divide by 16, and so we would get, and maybe multiply by 100, and then you have a percent. But the arithmetic is not, right, not critical. Okay, right, did everybody catch that? So we could convert the score from 0 to 16 into a score from 0 to 100 by dividing by 16 and multiplying by 100. But critical to the idea is the idea that for each test, we tested a binary classification, right? We had each beta value, and we asked which condition it was assigned. Once for the sad ones, once for the happy ones, right? And then iterate. Okay. So this is a basic classification analysis, right? In the sense that the stimuli, the category and set of stimuli that we trained on, we took new exemplars and used those as the test stimuli. But otherwise, they're interchangeable, right? It's new examples of the same classification problem. And so we ask, is there information that lets us learn and then test on this classification problem within this set of stimuli, right? For this distinction as implemented in this way within this set of stimuli. And that is, in some sense, the first clue that there's relevant information, but it's kind of a weak clue, right? Because anything that makes the female sad faces different from the female happy faces in this set of stimuli will lead to successful classification on average, right? So if, for example, by accident, the female faces are a little bigger, the sad faces are a little bigger or turned a little bit to the left or a little darker, any of those things in the stimulus set could be a reliable difference between these sad and happy faces that then gets propagated through this whole process, right? So this tells you that you can classify these stimuli, but it doesn't have very much information about why. Like what, on the basis of what can you classify these stimuli? Are you following this? Okay, and so it's important because this is a first test. It's an important first test, but it should not be the last thing you think of doing. It should be the first step of a classification analysis, where you say, yes, there is some information in the pattern that is related to this distinction, but the question we want to know is not some way to classify, but what information is there about that difference? And for example, you can see from this experiment, you might want to know, is it about emotions, right? That looks like an experiment we set up to study emotion understanding. But from knowing that you can classify these movies, you don't know that you can classify them because of a representation of emotion, right? All you know is that you can classify these movies. Feel clear on this? Okay, and so the other things I put on this list, generalization and representational similarity matrices, are both options for next steps to do after a first classification analysis as ways of asking, why can you classify the happy from the sad faces? On the basis of what feature? And is it the feature we were interested in, emotions, or is it some other feature? Okay. So the first thing that you could do is think, well, if this is a representation of emotion in faces, not of these particular videos, then if I had a new set of videos, just a different set of videos also depicting happy versus sad faces, then maybe I would still be able to classify it, right? And so in this experiment, for example, we also had male sad faces and male happy faces. We can take those movies out of the same experiment. And there's obviously two different things you could do here. One is you could do a whole different training and testing procedure. But what I'm advocating here is don't do a new training procedure, right? Just test on these movies. Does that make sense? So if you could just test on these left out movies, then what you're asking is, each time I learn a pattern difference that tells me the difference between the female sad and the female happy faces, does that pattern difference already generalize so that if you give it a male sad face, which in lots of ways is not going to look like the faces you trained it on, right? I mean, for a start, it's definitely a different identity, slightly different size and shape, etc., right? So it's a new image that has new other unrelated properties. Does that neural information that I learned about female faces, does it already generalize to male faces? If it does, then we start to think, well, maybe the pattern difference that we were picking up on, the relative activity in those different voxels, was whatever it was, it's in common between the difference between female sad and happy faces and male sad and happy faces. And that already gets closer to what we were interested in, right? Something that is about the difference between happy and sad, not the difference in the particular movies. Right, so the question is how much data do you need to train and how much data do you need to test? So yes, and why do we often have 8? Yeah. Okay, so if you have a given amount of data, you should use more of your data for training than testing, because you're more likely to overfit in training. So the reason why it's an asymmetric split, right? We don't take our data and split it in half, train on half, test on half. We put more into the training set and leave less for the testing set because you're more sensitive to overfitting in the training. So that is definitely a general principle, that if you're taking some amount of data for this kind of analysis, you will be more sensitive by putting more of your data in the training set and leaving less of your data in the test set than by splitting it half-half. And then in terms of whether 8 runs is the right number, you can just see, of course, that you would be less sensitive as you had fewer. And I presume that you could look at how does, in fact, I'm trying to remember if in this data set we looked at the function of how does the stability of our results as a function of the amount of data that we included per person, right? And for example, does it just keep going up and up and up, or is there some amount where you get close to a saturation for how much data you could have per person? My guess is you could probably always do better with more data, at least to some degree. Yeah, so I don't, again, this is bound to depend on the feature selection, the distinction, the region. But yeah, so I don't know off the top of my head whether there's a smallest number. Do you, Stefano, know if there's a smallest number of runs? Or for the number of folds, right? So it runs, okay, so here again, we're gonna go to a difference between the language in the math and the language in this cognitive neuroscience. This 7-to-1 ratio is called folds within the classification literature. So this is, right, we have 8 folds of the data. And those often in cognitive neuroscience correspond to runs, but they don't have to, right? So if you collected 2 really long runs, in principle, you could cut each run into 4 pieces. There's some issues about making sure that they remain independent of one another. So we could think about how you would want to analyze your data to make them independent chunks. But the main overarching thing is that it's a convenience for many reasons to have runs and folds be equivalent to one another, but not a requirement. But is 8 folds? No. Well, it could hurt. It can hurt if they are bad estimates for themselves for some reason. So we have tried using 5 runs in kids' data, training on 4 and testing on the 5th. It didn't work, but you never know why. The simplest sense is that there's no contribution of some common factor to both, other than the signal you're interested in, right? No shared noise factor in both data sets. The simplest way to worry about that in fMRI data is that, so one moment of fMRI data has a lot of history, right? So there's a lot of effects, sometimes called autocorrelation effects, right? That the measurement you make now is very predictable by the measurement you made in the previous TR for many reasons, some of them biological, some of them coming from the scanner. And so this is why if you're breaking up a single run, right, the time point at the end of the previous run is not independent of right before the break is not independent of the time point immediately after the break. And so if there's any shared history between those time points, you don't want them contributing to classification. But you could imagine if you had a long rest period in the middle, right, you could break in the middle of the rest and treat the data before that as long as you've modeled out run effects as relatively independent of the data after it. But this is, because of these issues, it's in general simplest if your folds are runs. Otherwise, you have to ask the question, do I know data in my different folds are equally independent? So for example, if you split runs in half, then this half of one run is less independent of the other half of that run than it is of your other folds, right? So there's different asymmetries between different parts of the data. And again, that you can think of ways of pre-processing your data to get rid of that, but it makes life easier if you don't have that problem to just collect your data knowing you're going to have runs. And then I don't know if everybody heard what Stefano said, but if you're going to do this, a piece of methodological advice, every run should have an equal representation of every condition, right? So if you're going to be classifying, for example, sad and happy faces, then every fold needs to have an equal number of the female sad and female happy faces. You don't want asymmetries in the training or testing set. And I don't know if you guys heard why. This is because, say 60% of your training set is sad, the classifier will learn, if you don't know what it is, guess sad, right? And so you want to make sure, if you're going to be doing a binary classification, that there's no such strategy coded in your training data. Yeah, so let's try not to go on to all the different ways to ensure and establish independence, but because I hope that most people won't. This feels like a problem you can avoid proactively by designing an experiment that doesn't have this problem. If you're trying to retroactively analyze data, then you can, I think, so there's various things like you can normalize your data by fold, you can, I'm trying to think if you could probably use scrambled labeled permutation tests, right? Data unscramble the labels. Right, so permutations would be conservative.
Yeah, exactly.
Right.
So they would not be.
But if you have too much of one condition, there's no reason not to drop some of it and train on a symmetric set. If you have 60% of one condition and 40% of the other, yeah, drop until you have a balance. But we're talking about beta values. Okay, this feels like a long trajectory into a weird situation, which ideally you just don't get yourself into, and then we won't have to solve it for you. Jaden, there's two separate questions, and let's separate them. One is, how do you do classification analyses if you have asymmetric samples in your classification set, right?
That's not the question.
Okay, yeah, let's leave that aside and then say, so the question of how well can you estimate betas in an event-related design where the conditions overlap and so the HRFs overlap, so you have to deconvolve them. That problem is not different for MVPA than it was for univariate analyses. And so all the same old rules apply. So for people who aren't familiar with these terms, when I showed you guys basic GLMs for getting the HRF for each condition, I put them as if they were really separate in time. So one condition's HRF would be over before the next conditions started. That's the way that very old fMRI analyses were done. But then people realized that can be really inefficient. You spend a lot of time doing nothing in the scanner. And so they figured out ways to bring events really close together, making the HRF overlapping. That became called event-related designs. And then how to pull back out those two separate HRFs from the overlapping signal. And this class was not intended to cover experimental design. That is solved in experimental design, right? So if you make sure that the timing and the contingencies between your event types are separable, that you can separate the HRFs, and then you get separate betas, and then everything else proceeds as normal on those separate betas. Yeah. The problems that you had to solve at the design phase, you still have to solve. You should still solve them. And then once you've solved them, come here with whatever you come to. Oh, one question I think Jaden asked, somebody asked me, is here I said we can test on the beta values for the whole run. Another option is to test on single trials, right? So that is, instead of taking one beta value for the whole run and having two things that you classify, you could try to estimate the response to each individual trial at test and try to classify that. And these choices about what is the unit of analysis, are we talking about betas for runs or are we talking about single trials? Those are options that different groups are using. They have different advantages and different disadvantages. So that's another option here, is to be testing on single trial responses rather than runs. For direct comparability, you'd want as much data here as you have here. So the simplest and most straightforward thing to do is to have, every time you test this in an iteration, you also test this. So in this experiment, we had an equal number of all the different trial types, right? And so every time we could test on one of the classifications, we could test on the same left-out run the other one, right? So the test trial data is all drawn from the same independent data. That's not the only way to do it, but it's a particularly convenient one. Okay, another thing I will just say about generalization. So this is a near generalization. What I mean by that is that happy male faces have some things in common with happy female faces other than being happy, right? They have particular shapes of configurations of the face. They have particular angles, right? Happy faces tend to be more up, whereas sad faces tend to be more down, right? There's a lot of things in addition to being happy or sad that are in common between the male sad and happy faces than the female sad and happy faces. So we have a version of the same problem we had before, a little bit less bad, right? So now that we know it generalizes to a new set of movies, we know it's not something really stupid about the training and testing on that particular set of movies, but we still might worry that it's not really the dimension we were interested in, it's some confounded dimension which you can classify. And I'm saying this again because I think in the euphoria around classification analyses and MVP analyses, one thing that has been missing is some critical evaluation of if a classification is possible, why is it possible, and is it based on an interesting feature space that we care about or some other feature of the stimuli, right? So again, in this particular experiment, what we did to deal with that is also build in a far generalization, by which I mean another set of conditions that we also thought would create the perception of somebody being sad or happy, but now in a way that should be as different as possible in every other way from the training movies. So this is kind of an idea of a stringent test. Are we right that this is a representation of people being sad or happy, independent of any surface feature, or as many as we could come up with, of what those movies look like? And so to test that, we had small cartoons of faceless creatures undergoing either social exclusion or social inclusion. Using a concrete example because I think it's easier to think through than in the abstract, right? I could have done all this with A's and B's, but it's harder to think through A's and B's. So this is not to teach you this particular paper, but just the logic behind it, right? So here, right, a little circle with eyes but no mouth goes up to a group of other little squares and triangles, and then either gets incorporated into the group or gets excluded and the group forms without them. So that should convey a experience in a way that is either negative or positive, but has no other configurational features in common with the faces, right? No facial change, etc. And so there the question is, okay, is it the case that a region where we could classify female sad versus happy from training on that, and also male sad versus happy from training on the female faces, does that very same pattern of information generalize to classifying exclusion versus inclusion? And so what I think is super cool about these data is that we found regions where we could classify in the faces, but we couldn't generalize to the cartoons, and other regions where we could classify in the faces and generalize to the cartoons. So to me, that pattern of results feels really cool in suggesting that we've been able to pick up on two kinds of information, both relevant to distinguishing sad and happy faces, but one of which is about facial configuration, or more about facial configuration, and one of which is more general to any information that's relevant for figuring out whether someone is sad or happy. And again, this lets you start to ask not only whether a brain region contains information, but something about what kind of information it contains, right? And both the positive and the negative result in the far generalization feel relevant to saying that, right? So something that can classify sad and happy faces but doesn't generalize outside of faces, that's cool. That might be something about faces, right? It might not be, but it could be something about faces per se. You keep testing it to find out. That, for example, the FFA could do that. The FFA could generalize across faces, but couldn't generalize to cartoons. Whereas in medial prefrontal cortex, we found that training in faces we could generalize to cartoons. In this case, we chose a bunch of regions, each and each region had been previously written about in literature as a region that had information about faces positive or negative emotions. So that was how we choose which regions we were interested in. The actual procedure we used was we used group functional data to set an anatomical constraint, and then within that, an SNR measure to pull features. Yes, if they are a family. So we haven't talked very much about multiple comparisons, but so in this experiment, we tested 6 brain regions. So if the question had been, in any one of those 6 brain regions, can we classify emotions? Can we classify positive versus negative faces? Then yes, you have done 6 tests. And so any one of those, you should correct for 6 comparisons if any one of them was interchangeable as a family of tests. This is the idea of what makes a family of tests for which you have to do multiple comparisons. This is a very fuzzy idea. This is one of those places where frequentist statistics sounds good until you get right into the weeds, and then sounds crazy the deeper you go. If you guys want a side note on families and multiple comparisons, we can certainly do that. But basically, yes. If your question was, in any of these 6 regions can we classify faces, then you have to correct for 6 tests. I just can't remember if we corrected for 6 tests, but I don't think it would have been a problem. I think these effects were pretty big. So here's one of these tricky things. You start with 6 regions. If the logic of your analysis goes like this, first, I will ask whether any of those regions can classify faces. If they can, I will ask whether they generalize. Then at the first step, you have to correct for 6 tests. At the second step, you only have to classify for as many tests as met the first criterion, right? If there's that hierarchical logic. This is one of the many cases where pre-registration can really help, because you can work through all of this logic before you know what the answers are. And so you can say things like, and this has come up in work we've done, we're going to test a bunch of different regions for this first property, and then any region that shows that property, we have a hierarchy of other things we want to know about, but that lets you do more sensitive tests within the regions you've decided you're interested in without correcting for comparisons on a whole bunch of other regions because you've screened them out at the earlier step. So Melissa said, say we were back up at the beginning, we had a classification result. So we could classify the female happy faces from the female sad faces. And I said, at this point, we have a question. Is it on the basis of some interesting deep high-level feature, or is it on the basis of some low-level confounding feature? And I said, one way to test that is do a positive control. Predict something else you should be able to classify if it was a high-level feature. And Melissa said, what about a negative control? So could we take those faces, preserve what we think are the low-level confounds, but disrupt what we think is the high-level information, for example, by flipping the faces upside down, right? So that keeps the brightness, the size, the motion, but might disrupt the perception of the emotion. And then say, if we can classify with upright, but we can't generalize that to the upside-down ones, is that evidence that the information supporting classification of the upright ones was the interesting high-level thing and not the low-level thing? And then she said, is that negative control less valuable because of the worry about null results in MVPA? So I think that the negative results remains valuable as a test of what the pattern is on the basis of which you could classify these faces, right? So if you're saying, look, there is a pattern of activation in these voxels, and it supports classification of these movements, then a negative control which says, does that pattern still show up for upside-down faces? If it doesn't, it means that was not what was supporting that pattern. So that feels to me like actually a negative control is useful in this context. The positive, yeah. So if you found a positive classification effect, I think it is useful both to do positive generalization tests and negative controls. Now, if you had to pick one between a negative and a positive test, I might pick a positive test because the predictive power of being able to do another thing, another positive thing, feels to me kind of cooler and harder than ruling out a set of control things. But the reason why it feels like a trade-off is, as you guys can see, this already takes data and a lot of time. It's a long experiment. If you're going to have both the classification, a near generalization, and a far generalization in a single experiment, that's already a long experiment. So if I were picking whether to add a negative control or a positive control, I might add a positive control, but I see value in both. Yeah. And if you got an unambiguous answer, right, that would be great. Like these, we can classify these in the presence of information about their emotions, very similar cases where you can't see the emotions, you can't classify, and look, it generalizes to some third positive case, right? That feels like a very nice package if you can have all of it. So this kind of conversation that you guys are having is exactly what we should have about any classification result, right? You see you can classify something, you start to wonder why, and you think, what are the positive controls, what are the negative controls, what are the predictions? So Ratan said, what if you held the stimulus constant, but somehow changed the percept? And so that would say, if we can classify the percept, even when we hold the stimulus constant, then we know it was something about what you saw, not the details of what we put on your eyes, right? So that's another technique that you could use. The way that we did that is we put unambiguous happy versus sad faces on the screen, but we told people either to pay attention to the person's emotion or to pay attention to their age. And then we asked, is our ability to classify emotions better when the emotions are task relevant than when they're task irrelevant? So that holds the stimulus constant, but varies the relevance of the features. And that is something, so there's been, we did that for faces, but other people have done that for objects. And one thing you certainly can do at many stages of the visual system, at early visual system, the ventral visual stream, is you can see that the features that are task relevant of a representation get enhanced. So it's easier to classify task relevant features than task irrelevant features. Yada Zhu at Harvard has really beautiful data showing that for objects in parietal cortex, you can classify any task relevant feature. If a feature is not task relevant, you can't classify it. So there's a representation in parietal cortex of stimulus features only if they are task relevant. Whereas in the ventral visual stream, there's a representation of object shape, which is there whether shape is relevant or not. So it's in her data, at least, it looks like a really strong dissociation between ventral visual stream, which has the shape regardless of task relevance, and the dorsal visual stream that has task relevance regardless of shape. In other people's data, the division is not quite as strong, and I don't know why there's that apparent difference. In any case, it is a thing you can do and super cool to look at how the representation of image or stimulus properties gets changed or enhanced when those things become the relevant feature. And it's cool, it makes you think about a model of what the brain is doing, right? That there's some set of features we're representing in a local region, but also whatever dimension of that is relevant for the task can be enhanced, can be made more prominent within the code we can see in fMRI, on the speed of tasks that you can do in the scanner. To me, that seems so cool that we can see that. The two streams are super duper interconnected in reality. So I think Yauda's hypothesis is that the ventral visual stream represents the shapes of the things that you see, and the parietal cortex maintains the representation of the thing you're using for your task. I just don't know how to make that fit with Krieger's data, in which the ventral visual stream representations themselves are affected by task relevance. That seems like asking the same question in the same way and getting two different answers. I don't know how to put those two together. But what I certainly can say for the purposes of an fMRI analysis class is that that's the kind of question you can ask with MVPA. And so that's great, right? Opens up a whole space of things that we would. So that's generalization. And the key thing that generalization was trying to do is make us ask not only whether there's information in a brain about some distinction, but what the information is, right? And the way we test that is by trying to think of other instances of the same distinction that differ from the training one in lots of ways, but implement this distinction we're interested in, again, in a new way. If the classification generalizes, then we think, okay, it must be the feature we were interested in, the one that let us generate these new predictions, that was the thing supporting the classification.